All right, going to do numbers 27 through 32 from chapter 15. So this is doing simple harmonic motion, but with special focus on energy considerations. Oops. All right, here we go. 27, when the displacement in simple harmonic motion is 1/2 the amplitude. So I'm just going to make a little sketch here. So when the displacement is 1/2 of the amplitude, like right here, then what fraction of the total energy is kinetic and what half is potential? Well, here, I know that the total energy is equal to, right here, the velocity is 0, right? So all of the potential energy is in the spring. So it's 1/2 Ka squared. That's how much total I have. And if that's the total everywhere, right? So here I have some potential in the spring and some kinetic energy. But I do know that these two things have to add up to that, because that's the total amount that I have. So I don't know how fast it's going here, but I do know this is easy to do. This is just 1/2 K times A over 2 squared. And if you do all that out, that's 1/8 Ka squared. And that means that the rest of it, 3/8, because 1/8 and 3/8 adds up to 1/2, has to be kinetic energy. So when it's at this halfway point, it's not, I mean, you might just guess right off the top of your head, oh, it must be half and half. But it's not half and half because of the x squared in the 1/2 kx squared. So it's a 25%, 75% split. So the answer for A, what fraction is kinetic energy? That would be 0.75 or 75%, and then 25% there. And for part C of that, what displacement in terms of the amplitude is the energy of the system? Is it half and half? Well, half of the total energy would be 1/4 Ka squared. So we would be looking for what is if that is half of the total energy, then I want to know what is the x value that gives me that much, right? So just doing a little bit of math here, the k's cancel out, the 1/2, so that's 1/2. So it'd be the amplitude divided by the square root of 2. Or if you don't like that, then square root of 2 over 2 times the amplitude. All right. 28. We got a graph here. It gives the one-dimensional potential energy well for a 2 kilogram particle, and they're just telling us that it's a bx squared, so it's definitely a 1/2 kx squared kind of thing. It's just that they packaged this as, they said it was b, whatever. I don't think that matters. And the vertical axis is 2 joules. If the particle passes through the equilibrium position with a velocity of 85 centimeters per second, then will it be turned back before it reaches x equals 15 centimeters? So we want to find out how much energy it has. And go from there. So let's see. How much energy does it have at this equilibrium point? At the equilibrium point, that's where there's no potential energy. It's all kinetic energy. 1/2 mv squared. Got a calculator around here somewhere. There it is. One half mv squared. Okay, so that's the total mechanical energy, because here this is 0, this is 0.72, so that's the total. So now, if we look at the graph, I'm going to scoot that in here. If we look at the graph, then where is that? If this is 2, 0.72 and 15, it looks like we are going to make it. We will be turned back, because that's the max there. So I think I'm going to need to find the equation for this thing to be able to solve this. So they told me that u is equal to bx squared, and if I just pick some points on here, it looks like at the point where x is equal to 20 centimeters, the u is equal to 2. So b is 50. So that equation for that potential energy, I mean it is a spring, right? It's a 1/2 kx squared, is equal to 50 times x squared. And this is the total amount of energy that I have, right? So if all of that energy, all 0.72 of it, is given over to the potential energy, that will be the maximum x position that it can get to. So that is 0.12. So can it make it to 15 centimeters? No, it's only going to make it to 0.12 or 12 centimeters. So no is the answer to part A, and then part B, that's where it makes it to. Number 29. Find the mechanical energy of a block spring system having a spring constant of 1.3 newtons per centimeter. Which is 130 newtons per meter. I think I prefer those units. And has an oscillation amplitude of 2.4 centimeters. I'm going to change that to meters. And we want to know what the mechanical energy is. Well, the total mechanical energy is equal to the kinetic energy when it's in the middle, and the potential energy when it's at its maximum amplitude, right? So the potential energy at the maximum is 1/2 K A squared, and that is the total. So mechanical energy total is 1/2 K A squared It looks like 3.7 times 10 to the negative 4 joules. Right. I think we're good there. Oh, no, we're not good there. Because I used the wrong number here. I used the 1.3 instead of the 130. So that's not getting squared or anything, so I just need to multiply that by 100. Sorry about that. That's fixed now. So that's 3.7 times 10 to the negative 2 joules. That's better. Let's see if we can squeeze 30 down here at the bottom. An oscillating block spring system has mechanical energy of 1 joule. And so remember, that could be set equal to 1/2 mv max squared, or it could also be set equal to 1/2 k times the amplitude squared, because at the maximum, it's all kinetic energy at the Vmax in the middle when x is 0, and when x is maxed out at the amplitude, then that's a turnaround point, so it's all potential energy. So let's see what we have here. It's got an amplitude of 10 centimeters and a maximum speed of 1.2 meters per second. And we want to find the spring constant, mass of the block, and the frequency. So that is equal to 1/2 Ka squared. So 1 is equal to 1/2 Ka squared. So let's see, that's 200, right? Yep. So 200 newtons per meter is the spring constant. B, we're finding the mass. So that 1 joule is also equal to this. The V max is 1.2. It's about 1.39 kilograms. And C, the frequency of oscillation. I'm going to find the period, and then I'll flip that over. That'll be equal to the frequency. So period is equal to 2 pi times the square root m over k. So that's that. That'll be seconds. And then I'm just going to, this is the flip it over button on your calculator, right? X inverse. Just going to invert that. And that's about 1.91. And that's either inverse seconds or you can write it as hertz. Correct, either way. All right, 2 more. If we can beat the announcements here. Number 31, 5 kilogram object on a horizontal frictionless surface is attached to a spring. The spring constant 1,000. newtons per meter. Object is displaced from equilibrium 50 centimeters. And given an initial velocity, so that's not the amplitude, that's just some x, because it's also given an initial velocity of 10 meters per second back toward the equilibrium position. What are the motion's frequency, initial potential energy of this block spring system, initial kinetic energy, and the motion's amplitude? All right. So the frequency is going to be, period is 2 pi times the square root of m over k, and I've got that, right? So I can do that and then flip it over to get the frequency. Let's see, so that m is 5, and the k is 1,000. I'm going to flip that over. So the frequency is 2.25 hertz. And for B, looking for what's the initial potential energy? Well, that is 1/2 kx squared. I didn't say ka squared because this is not the amplitude. The amplitude is going to be bigger than that because they've got a extra kick there. 1/2 1,000 times 5 squared. I think it's 125 joules. And then C, what is the initial kinetic energy? 1/2 mv squared. That's 250. And part D, what's the motion's amplitude? So if you want to know the amplitude, well, that's when the 1/2 ka squared is equal to the total mechanical energy, right? Where the turnaround point, that's going to be where the velocity is 0 and all the energy is potential. So 1/2 k a squared, total mechanical energy is 375, right? Sum of those two. And let's see, so at the square root of 375 over 500, that's about 0.87 meters. Here we've got kinetic energy graph of a simple harmonic oscillator versus position. The vertical axis is at that, Ks is at 4, so that maximum point there is actually at 6. I hate it when this book does that. I don't know why. But if you look carefully, that Ks, that they have scaled at 4, our maximum is at 6. So the total mechanical energy is 6 joules. That's when it's maxed out as kinetic energy. What's the spring constant? And the amplitude is equal to 0.12 meters. You can see that's where the kinetic energy goes down to 0. Right? So total mechanical energy is equal to 1/2 a squared, and I think that's all we need. It's also equal to 1/2 mv max squared, but I think this is the relationship that we need, because I know from the graph that total is 6, 1/2 k, and I've got the amplitude, so that's it. So whatever 12 divided by 0.12 squared is, that's it. All right, not too bad. Those seem to get easier as we went. I don't know why they set them up in that order, but that first one, I don't know, first and second one seemed to be a little trickier. So I don't know, maybe I was just getting warmed up.